actually going to define this object graphically or geometrically. All right, 5.4, 5.3. Okay, so we're going to talk about definite integrals. Okay, definite integrals, and well, some of you have my notes. You know what I'm going to get at here. Well, leave it as a small secret. Not much of a secret. All right. Introduction. All right. So what's the deal with a definite integral? First of all, how does a definite integral look different? All right. Example. Okay. Now here I had the indefinite integral of x squared dx. Okay. Here is the definite integral from 1 to 5 of x squared dx. So that's a telltale sign that you have a definite integral. Okay, as Jeff Foxworthy might say, you might have a definite integral if you have numbers over here and over there. Okay. The one here is called the lower limit of integration. Okay, and by the way, these are related to sums, as we'll see. So it's kind of like, summation can have a lower limit. Similarly, the integral has a lower limit. Okay, 5 here is the upper limit of integration. Okay, the integral from 1 to 5 of x squared dx. All right, what is this? This is the definite integral of x squared from x equals 1 to x equals 5 with respect to x, the variable of integration. One note, we say from x equals this number to x equals that number, okay? This is the integral from 1 to 5, not from 5 to 1.
Is it similar to sigma notation?
We are going to, okay, we're going to, right now we're going to define this in terms of geometry and areas. That's the key word, areas. Okay, and then we're going to relate this to sums. Officially, we define a definite integral as a limit of Riemann sums. Okay, so that summation thing, there's a direct relation. In fact, some people think that that curly thing is like S for sum. Or super. All right.
What's the WRT?
With respect to, that indicates a variable of integration. Now bear in mind, in Calc 3, you are going to get situations where you might have an x there and a y there, so that's why you have to be careful. You have to indicate the variable of integration. And you remember the chain rule and composite functions, the differentiation. Okay. Well, I just gave it away. Definite integrals and areas. And in chapter 6, we talk more about area. Right? All right. So, bottom line, well, I'll just draw this out. Okay, x-axis here, y-axis here. Okay, if we graph y equals x squared, we get a parabola, but we only care about the piece of the parabola, y equals x squared, from x equals 1 to x equals 5. All right. So, the value of the definite integral is going to be the area right in here. Okay, it's the area between the graph of y equals x squared and the x-axis. And the reason why this works is because x squared is never negative. Okay, if x squared is sometimes negative, then we have to take that into account. Okay, bear in mind that this works because x squared is non-negative on the interval. In fact, it's non-negative everywhere. For all real x. Okay. But certainly, if you have a non-negative function that's continuous everywhere, as it turns out, then if it's non-negative everywhere and it's continuous, then the definite integral, okay, will always correspond to an area if we're going from the lesser number to the greater number. So for right now, we're assuming that the integral is going from the lesser number to the greater number. Although later on, we will talk about the integral from 5 to 1, for example, or from 10 to 3, okay? Those are legal. All right. kind of postponing this because I wanted to build up to this. Remember back in chapter 3, we introduced derivatives, right? Now, graphically, a derivative was a what of a what line along the graph? Slope of a tangent line. Okay, so it's kind of like we're getting smaller, right? We're taking slopes of tangent lines. Integrals are kind of getting bigger. What do you mean by bigger? We have the graph, and we're considering not slopes of tangent lines, but areas, these big old areas. But again, there is a natural geometric interpretation, particularly when the function is non-negative, and by the way, continuous. We do like them to be continuous. All right. It turns out, you don't know this yet, but it turns out, using methods from section 5.6, all right, this is 41 and a third. Okay, why is it 41 and a third? You'll figure out how to do it later on in 5.6. Later this week we're pretty much doing chapter 5. The very last section next Monday. Your test is 2 weeks from now.
Monday?
2 Mondays from now. We do almost all of chapter 5 this week. We do that last section next Monday. I start at 6. I continue at 6. Take questions next Wednesday. Your test is 2 Mondays from now. Which is an eternity compared to the gaps you get after chapter 5. Be forewarned. It's coming faster. All right. You get a 46-hour gap between the chapter 7 test and the final, so be prepared. All right, that's coming faster. Okay, and by the way, when I say area, you don't need units. Okay, so if you just see a raw definite integral, there's no word problem context, then there are no units. Okay, of course, in another word problem context, you might have units, like dollars or something. We'll talk about that. Okay, but any questions? So your answer to an indefinite integral problem is typically a family of functions, right? Or rules, like x cubed over 3 plus c, something like that. Your answer to a definite integral problem is typically a number, something like 41 and a third. Okay? If it's a word problem, then you might have units, like dollars or something. Any questions?
Why is it called a definite integral?
Okay, well, basically we have definite integrals versus indefinite integrals. Okay? So the indefinite integral, you're describing this family of antiderivatives. Okay?
Oh, okay.
And with the definite integral, you're getting particular numbers. They are related. Now, in 5.6, we're going to talk about how you get this number. Okay, how do you use this information, okay, to arrive at this number? It's called the fundamental theorem of calculus, and that is important, as you can tell. The fundamental theorem of calculus. Okay, what does the fundamental theorem of calculus do? It tells us basically how we use how we use indefinite integrals to work out definite integrals. Because the way you work this out is to use antiderivatives and indefinite integrals. They're going to connect in 5.6. Right now you might be going, well, what does that have to do with each other? How come we're using the integral sign? Right? Where are derivatives and integrals coming up? We don't see the connection yet. In 5.6 we connect them. Okay? Because you might be going right now, wait a minute. Before, without the numbers, when it was indefinite, we'd say x cubed over 3 plus c. Well, where does that come up? How does that get us to 41 and a third? We'll talk about that in 5.6. That's what connects them. Okay? So, indefinite integrals, definite integrals, they're going to connect in 5.6 Wednesday. Okay? And then you can actually work out this simple problem to get that number. All right? So, they are going to connect. Again, when you have a definite integral, when you have these numbers here, lower limit, upper limit. Okay. Although you could have, an A or B or whatever. You could even have X for some fixed X. Yeah.
Even if there's a big range between the upper and lower limit.
That's okay. Integral from 1 to a million. Why not? Yeah. In principle, it's no different from this. Just go for it. All right. Another example. Okay. We'll take a look at this. The integral from 1 to 5 t squared dt. Well, if my answer to this is 41 and a third, what do you think my answer to this is?
41 and a
Yeah, it's the same, 41 and a third. Okay, why is that? Because if I just change the letters, right? So here's the t-axis, y. Okay, here's y equals t squared, from t equals 1 to t equals 5. You agree it's going to be the same area, right? So it shouldn't matter how I label the horizontal axis, right? It could be integral 1 to 5 grandma squared d grandma. It doesn't matter. It's going to be 41 and a third. Okay, you're integrating the squaring function. Of course, you have to be consistent here, right? You have to have the same variable there, right? For this reason, we sometimes call the variable of integration a dummy variable. Okay. So here, in fact, x over there, t is a dummy variable here. It's like politics. If you replace one dummy with another, nothing ever changes. So, so it is a dummy variable. It doesn't matter what it is. What matters is we're integrating the squaring function. Okay? That's only marginally relevant, just a technicality. We're integrating the squaring function from 1 to 5. All right. It's just like in summations, right? The index of summation. It doesn't matter if you're summing from I equals 1 to 3 or j equals 1 to 3, as long as you make the letters consistent. Okay. All right. Okay. Just some comments. I'll make an area comment. All right. Now, just on the basis of this geometric interpretation, technically it's an interpretation. We're not going to define this officially until later. All right. But the thing is, the geometry helps before we even define it, because then the definition, if we didn't do it that way, the definition would have no motivation. Okay. So right now it helps to think geometrically, what we're kind of getting at. All right. Example. Integral from -2 to 3 of 2 dx. Okay, the integral from -2 to 3 of 2 dx. Okay, whether you do it the geometric way or the fundamental theorem way, this is very easy, as you can tell. All right. Well, let's do this in terms of areas. Let's do it in terms of areas. All right. Here's the x-axis. Here's the y-axis. How do you graph y equals 2? How do you graph that?
So,
Line, horizontal line. Okay. So it's a horizontal line. Y equals 2. We go from x equals -2 to x equals 3. And yes, it does matter that we go from the lesser number to the greater number. So for right now, we're going from the lesser number to the greater number. -2 to 3. Again, it's not 3 to -2. It's -2 to 3. All right. And I find the, what's the A word again? Area. So come on. You have a rectangle. Okay. Now, of course the height is 2. That's not the tricky part. The tricky part's the width. Okay, what's this base here? It's going to be 3 minus -2. That's 3 plus 2. That's 5. Okay, so here, B minus A is 5. Okay, that's the width of that block there. All right, so what's the area? It's going to be 5 times 2 is 10. All right, so the value of that definite integral is 10. Again, your answer to a definite integral problem is typically a constant. Right? In this case, 10. It's not a family of functions. Questions? Questions? We're just interpreting things in terms of areas. Here it's good to know that we just had a rectangular block. All right. There's some problems where the geometric interpretation is the way to go, even if you know a lot of calculus. All right, example. Integral, -1 to 1, root 1 minus x squared dx. All right. Now, in Calc 2, you're going to learn how to do this mechanically, but the geometric way to do it is the way to go, because this is very easy geometrically. But here's the question. Do you remember what the graph of y equals root 1 minus x squared looks like? It's half a what? Half a circle. Remember that? Half a circle. If you don't remember it, let's rewrite this. Square both sides. Y squared equals 1 minus x squared. How do you make this equivalent? Remind yourself that y has to be non-negative. Add x squared to both sides. X squared plus y squared equals 1. Again, y has to be non-negative. Okay, so this here is equivalent to that over there. What's the graph of x squared plus y squared equals 1? It's the unit circle, centered at the origin. But wait a minute, y has to be non-negative. Which piece am I taking? Only the top piece. Alright. So forget this stuff over here. I'm only taking the top piece. This goes from -1 to 1. Alright, I get a half circle. And you agree that we can figure out its area, right? The area of this semicircle. We only go down to the x-axis, not below. Right now we're not going down below. We agree this is non-negative. the interval here. By nice, I mean continuous. We'll talk about that. All right. So how do I find the area of that yellow blob there? Okay, first of all, what's the area of a circular disk? Pi r squared. Pi r squared. But wait a minute, we're only picking up half the circle. 1 half. What's the radius of the unit circle here? 1. Radius is 1, right? Okay, so 1 half times pi times 1 squared. Well, that's just pi over 2. Okay, no units, pi over 2. Okay, so the area of that semicircular region, pi over 2, that's the value of that definite integral. Any questions? Any questions? We're relating definite integrals with areas. That's the key application. In a way, I'm almost defining these things in this fashion.
Question?
Yeah.
Can you do without the formula?
You mean without a geometric formula? Here's the thing. You would take calculus 2. You would set x equal to sine theta, dx equal cosine theta, d theta, and then eventually perform a trig substitution. This is good for now. In fact, that is a trig sub. That is a trig sub. X is sine theta, dx is cosine theta, d theta, and you work it. Okay, and then you use right triangles to get back to x. Do it, and you'll get the same answer. Actually, that's a good challenge. No, don't blame him. I'm saying as an optional step, do it. Let x be sine theta, dx be cosine theta, d theta. Work it. Use right triangles to get back to x. It works. All right. Okay. All right. Issue B. What happens if the function sometimes or always goes negative? Okay, then we talk about signed areas. Okay, now remember, areas themselves are never negative, but sometimes we sign them. Just like in trig, sometimes you sign side lengths if you're in different quadrants, besides quadrant 1, right? Okay, so for example, let's say I give you a function whose graph looks like this. Here's little a, here's little b. All right, let's go like this. I'm big enough anyway, but all right. So let's say the graph goes like that. All right, here's the graph of y equals f of x. All right. Problem is it's sometimes negative. So how can we interpret we could even define it this way. The integral from a to b f of x dx. And by the way, that is the generic form for a definite integral. The integral from a to b of f of x dx. For now, we assume a is less than b, but we'll relax that later on. Okay, so again, for now, we're assuming that a is less than b. All right. Based on this picture, what do we do? All right. Let's say that this area is capital A. Let's say that this area is capital B. Let's say that this area is capital C. What's the value of this definite integral? Well, we take A plus C minus B. Okay, I'll write it like this. We add A, the area of that first chunk there, but we subtract B. So we're basically subtracting the contributions corresponding to regions below the x-axis. Okay, and then plus C. So basically, you have to keep track of when you're above the x-axis, or whatever axis, and when you're below the axis. Yeah.
Why is it called signed areas?
In the sense that, for all practical purposes, this contributes the opposite of b to the definite integral. Okay, so in that sense, the signed area of that region is negative b, or the opposite of b. Even though technically areas themselves are never negative, just like with lengths. But in trig, sometimes we put negative signs on those lengths, right? Your quadrant 3, right? Sometimes we put negative numbers on those lengths. Okay, this is very similar. Right? So remember, regions below the axis, that horizontal axis, contribute a negative value to the definite integral, which means that the value of a definite integral could be positive, could be 0, could be negative, okay? Or could be undefined. And that won't happen in this class, though. That might happen in Calc 2, but not in this class. Okay, I will not give you an integral that's undefined in this class. For Calc 2, yeah, you'll see some undefined integrals. For example, cosine of x.
It's equal to 0.
Okay, right? You go from here, 0. Here's 2 pi. Okay, now assume that I've drawn this well. Okay. What's the value of that definite interval?
0.
It's going to be 0. Right. Explain to me why you think it's going to be 0.
Because the top and bottom is even.
Yeah, this area here, yeah, symmetry here, this area equals this area, but this provides a positive contribution, this provides a corresponding negative contribution. And as it turns out, this is positive 2. I think I made that note here. Yeah, it turns out that the area here, and you can work this out in 5.6, this turns out to be positive 2. Okay, the area here is 2, contributes positive 2. The area here is also 2, but it contributes a negative 2. When you combine them, we have 0. So they cancel each other out in a sense.
Does whether the interval is open or closed, does that matter?
Then you get into measure theory. Let's talk about closed intervals. Okay, so assume this is a closed interval. I'm not going to mess with you on that. Okay. I will say that if the integrand is continuous on the closed interval, then you will have a value for the interval. On the closed interval, then you will have a value for the interval. Okay. I'm not going to mess with you in that sense. Although I may have you state the MVT for integrals, which we will talk about on Wednesday. Let's do another example. The integral from -1 to 1 of the opposite of root 1 minus x squared dx. All right. Gives you a hint here. How do you graph y equals that guy?
The bottom is
Bottom half, going from -1 to 1. The area for that top semicircular region was pi over 2. The area here is also pi over 2, by symmetry. But then, what's the value of that integral? It's negative pi over 2. Why? Because the entire region is below the x-axis. Yeah, below the horizontal axis. Answer here is negative pi over 2. There's another way you could have done this. See this -1 factor? Pop. There's linearity. The -1 factor pops out. It's pi over 2 there, right? So you could have done it either way. Like I said, the value of a definite integral can be positive, 0, or negative. It will not be undefined until count 2.
I have a question. For the previous example, are you going to give us it's 2 or? How do you
Oh,
know
okay,
it's
now
2?
for your chapter 5 test, you'll be able to figure this out all on your own by using the fundamental theorem. I got that this was 2 from the fundamental theorem. You don't know
Okay,
that.
we don't know.
Yeah, you don't know that yet.
Okay.
Okay, but aside from the FTC, I don't know how else you would do it unless you use the FTC. Questions? These things can happen, okay? The value can be 0, can be negative. That can happen.
So we're gonna need to know basic graphs to do this section.
Yes, nothing beyond my pre-calc. Yeah. So again, you might want to review my chapter 1, 1.2. 1.3. Okay, your basics. Now bear in mind, in chapter 6, when we're talking about areas and volumes, you're going to have to know those graphs anyway. So, why not now? Go ahead and review those basic graphs. And in fact, we're going to see cylinders and cones in chapter 6 scale. All right. Let's talk about some properties. Okay. So we'll talk about some properties. We're back from Ren Stiffy properties. Yeah.
With these problems, would it only be like cosine or sine? Like what about like cotangent and tangent?
Ooh, okay. Now remember, in 5.6, we're going to link these with indefinite intervals. So the question is, can you take the indefinite interval of the guy? So ironically, if we have the integral of secant squared x, and it's nice on here, no dA's in the middle. That's not 2. Okay, but if this is like secant squared x actually, where these are nice, like for example, pi over 4 to pi over 3, we can do that. Like secant squared x, we can do that. Secant x we can't do yet, because we don't know how to integrate it yet. Chapter 7 we will. Alright. So it depends. Can you do the indefinite? We'll go over some properties, and then we'll take a break, and then we'll talk about ways to approximate these intervals, and then how to formally define them using the limits of Riemann sums. All right, which is really the way you're supposed to introduce them, but this is much more natural. All right, let's finish before the break with some properties. Some properties of these definite integrals. All right. Example. All right, what's the integral from 3 to 3 of x squared dx? So if I take the graph of y equals x squared, all right, what's the area of that line segment? 0. Okay. And in general, the integral from c to c, this is not to be confused with the plus c that comes before, but the integral from c to c of f of x dx is going to be goose egg, 0, okay, if f of c exists. There's literally a proof. Right. So the integral of a function from a number to itself is 0, provided that that number is in the domain of the function. Okay. Basically, the area of the line segment is 0. All right. This next one, well, it makes our other rules consistent. All right. The integral from 1 to 5 x squared dx, I told you was 41 1/3. You'll be able to prove that after Wednesday. It's an easy problem once you see what happens on Wednesday. All right. Now, and this is partly for consistency with what we're going to see later on. What's the integral from 5 to 1 x squared dx? Guess what we're going to make this? Negative 41 1/3. Basically, if you switch the limits of integration, you're going to flip the sign. And this allows us to be consistent with other forms for adding integrals, for example. All right. So in general, the integral from b to a f of x dx is the opposite of the integral from a to b f of x dx, okay, if these integrals exist. If these integrals exist as constants, real quantities. Right. Okay. So in this sense, we can now talk about the integral from 10 to 3, or the integral from 5 to -2. We can do things like that. All right. And then for the geometric interpretation, we play this game. All right. Okay, questions about those? We'll talk about more properties later on. All right. And okay, after the break, we're going to approximate definite integrals. Okay. Approximating definite integrals. Basic numerical analysis. All right. And in fact, if we don't know the indefinite integral, then we may be forced to use a computer method, the approximation method. All right. Okay. So let's go back to our example 1. Okay. What is the integral from 1 to 5 x squared dx? We're going to see an exact method on Wednesday, but how would a 4th grader approach this? All right. Well, let's consider the graph here. X, y. Let's consider the graph of. Okay. Let's let f of x be x squared. That's the integrand. All right. We're going to graph the integrand. All right. Y equals x squared. Y equals f of x from x equals 1 to x equals 5. All right. Now, the 4th grader may not know what he or she is doing, but we can call the method that we're using here an LRA. What's an LRA? It's a left-hand Riemann approximation. I don't think the 4th grade would call it that, but that's what we're going to call it. All right. A left-hand Riemann approximation after Riemann, 19th century Germany. All right. Left-hand Riemann approximation. All right. Using the following partition. Okay, using the partition, technically we use the cursive P more often, but the cursive P, all right. Using the partition P of the interval from 1 to 5, closed interval. So technically it's a closed interval from 1 to 5, all right, where P goes like this. actually only at 4 of these 5 places. Okay. So here's the idea. We're going to break this interval up. Okay, the main interval is from 1 to 5. We're going to break it up into a bunch of subintervals determined by that partition. All right. So, all right. Here's 2. Here's 3. Here's 4. All right. 1, 2, 3, 4, 5. All right. Here's what a left-hand Riemann approximation does. Now, the idea is that a 4th grader might not know how to find the area of this kind of curly wedge thing, but a 4th grader knows the area of a rectangle. I hope you all know how to find the area of a rectangle. So we're going to use rectangles to sort of tile this, to approximate the total area of the region. All right, so we have here 4 subintervals. Okay, so this partition determines 4 subintervals. Okay, 4 subintervals. Okay, from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. And they're surrounded by these 5 kind of fence posts. All right, so here's the idea. In the first subinterval, all right, the kid is going to stand at the left endpoint. Okay, so on this subinterval from 1 to 2, the kid's going to stand at 1. Okay, and then look up the stars. Look up at the point that's on the graph. All right, at this point here, and then draws the rectangle with that height. Okay, and it's as wide as this first subinterval. So that's the first Riemann rectangle in an LRA for this problem. The second rectangle, okay, we look at the second subinterval from 2 to 3, all right? The kid's going to stand at 2 because it's a left hand, all right? So the kid's going to stand at the left endpoint, looks up, and over. Okay, by the way, this is not to scale. In fact, I should have drawn this way lower. All right. Between 3 and 4, okay, kid stands here, looks up and over, all right? 4 to 5, kid stands here, looks up and over. All right. Now, we can use the sum of the areas of those rectangles to approximate the area under the curve. Now, when we do that, is this going to be an overestimate or an underestimate of the true answer? It's going to be an underestimate because we're going to be missing these gaps. Okay, in fact, there's a big one at the end here. Okay, the biggest one's at the end. The gaps get bigger and bigger. All right, so it is going to be an underestimate. All right, but it is a scheme, right? It's a way for a 4th grader to do an approximation without knowing any calculus. All right, so then, how do we work out the calculations? What does this look like then? Okay, so the L array here will look like this. The L array will look like this. All right. All right. So how can we designate the area of this first rectangle over here? All right. Well, remember this is the graph of y equals x squared, or the graph of y equals f of x. All right. Now, how can we indicate the height of this rectangle? Well, f of 1, right? That's the y coordinate of this point here, right? It's going to be f of 1. All right. F of 1, that's the height. Okay, the sine height, I should say. The sine height of the first rectangle. Bear in mind that if the graph is going below the x-axis, then we count a negative function value, and that's legitimate. Okay, because that contribution will be negative, right? Times the width, but here the width is just 1. Okay, still I'll indicate that. Okay, times 1. Okay, this is the width of that first rectangle. But you agree that f of 1 times 1 is going to be the area of that first rectangle, right? It's given by the y coordinate at that point times the width of the subinterval. Any questions? Any questions? Plus, okay, well, how's this different? Okay, well, what's this height designated by? F of 2 times 1. Okay, here I'm spoiling you, I'm making the width 1. Okay, and so forth, right? Plus f of 3 times 1 plus f of 4 times 1. Okay, again, I'm spoiling you because the widths here are all 1. Okay, so I'm going to indicate that just so you can generalize. Okay, and then how do we evaluate the function? Well, it's just a squared function. We plug it into there, right? Okay, so f of 1 is 1 squared, okay, times 1, plus f of 2 is 2 squared, times 1, plus f of 3 is 3 squared, and then times 1, plus f of 4 is 4 squared, and then times 1. All right, so what are the areas here? Well, what's 1 squared times 1? That's 1. What's 2 squared times 1? 4. What's 3 squared times 1? 9. And what's 4 squared times 1? 16. Okay. And bear in mind that we don't have to do 5 plus 16, that's going to be 30. All right. And that's our L array if we use this. It's a regular partition, by the way. I might mention that somewhere. This is a regular partition. This partition P is regular because we have equal widths. Okay. And we have n equals 4 subintervals. Right. So for this L array, okay, with respect to this regular partition, using 4 subintervals, n equals 4, we end up with 30. And what was the answer I gave you? I told you that the exact value of this was what? 41 and a third. Yeah, that's way underestimate, right? Okay. Okay, so 30 is way below 41 and a third. All right. But that's an example of an L array. An L array. I put a big 1 here, I guess. Scheme 1, an L array. Any questions? Yeah.
Could you make more sub-intervals to get
Yeah.
a better
Like if you want, well, okay, now remember, we start at 1 and end at 5. Like I said, you could go 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 5. In which case, you'd have 0.5, 0.5. You'd have more of these than 0.5s as your width. You agree that would be better?
Yeah.
That gives a better approximation. But the price we pay is that we have more things to compute and add up. All right.
Can we do the same thing on the top of the curve and then like average it?
Yeah, yeah. In fact, now we're going to think in terms of left and right. So Kautsky thinks in terms of, I think, inscribed and circumscribed. So he thinks about it a little bit differently. But we're going to think in terms of left and right. And the right hand, we're going to do the right hand. Okay, just a moment. Any other questions before we do that? Yeah.
On the example, you gave us like the intervals that we're supposed to use for the approximation, or will you ask us to make our own interval for the approximation?
No, you'll know what to do. So I'll either give you the step size, the interval width, or I'll give you the partition, or I'll give you the number of subintervals, in which case you need to figure out where to place your marks. All right. Anything else? Anything else? People tend to do a good job with these because they know what to do. All right. We'll see, get some practice. Now, speaking of Paul's point, let's go ahead and do an RRA. All right. What's this? Number 2. What if we do an RRA? Okay, that's going to be a right-hand Riemann approximation. Okay, and this sounds like The Simpsons, R-E-R-R. Okay, right-hand Riemann approximation using the partition. Okay. All right, now how does this picture work? X, Y. Okay, I should make this smaller. Okay. All right, so y equals f of x, y equals x squared. All right, going from x equals 1 to x equals 5. Again, here's 2, here's 3, here's 4. Okay, so again, we're going to have n equals 4 subintervals. This time we're going to do a right-hand Riemann approximation. So we look at the first subinterval from 1 to 2. Where does the kid stand? At the right endpoint, which is going to be, well, okay, between 1 and 2. Between 1 and 2. 2. Okay? Bear in mind, when you do a Riemann sum, in principle you can stand anywhere in here, but we're going to set up a pattern, right? So we're always going to stand at the right endpoint of each subinterval. We stand at the 2 here, all right? We look up. This time we go left and down. All right, and you agree that we're going to do an overestimate over that interval in that case, for this function. Now, if it were a decreasing function, then it's flip-flop. Yeah. Okay. But since it's an increasing function, this is going to be an overestimate over here. All right. Between 2 and 3, where do we stand? We stand at 3. We look up to the left. 4. 3 to 4. We're 4. We stand at 4. We look up. Left. Down. So it's kind of like these rectangles are being moved over one, and the smallest one got knocked out. And look over here. Mix this up. 4 to 5. We stand at 5. We are going to pick up this point way up here. Left and down. Okay, so this time we're going to pick up this big rectangle over here. So we knocked out the smallest rectangle, and we bring in this biggest rectangle. These got translated over 1 unit. All right? And you can tell these calculations will be different. But how will the calculations be different? All right? Well, we're going to delete the f of 1 times 1 guy. what's different here? Okay, so for the RRA, okay, we're gonna delete that f of 1 times 1 guy. We start with f of 2 times 1, right? Then f of 3 times 1, f of 4 times 1, and who's at the end?
F5.
We have f of 5 times 1. Okay, again, if the widths were like 1/2, we put 1/2. Okay, again, I'm spoiling you by making the widths all 1 here. All right. Okay, so what do we get here? Okay, this time we're going to get 4 over here. 2 squared times 1 is 4. 3 squared times 1 is 9. 4 squared times 1 is 16. And what's 5 squared times 1? That's 25. All right. And what's the sum of all these guys? All right, it's going to be 54, right? Very different. So the right-hand Riemann sum is 54. That's obviously an overestimate because we're picking up these excesses over here. All right. Any questions about that? Any questions? Bear in mind, for a more difficult function, we may not know if it's an overestimate or an underestimate, especially if we don't really know its graph very well. Okay, so this might be good for experimental situations where you want to approximate an integral, but you don't have a closed form for f of x. You don't have a nice rule like f of x equals x squared. You're just taking lab results and doing an approximation. All right. Okay, now Paul, you did suggest something. Take the LRA, take the RRA, and do what? You know, average them, right? And it turns out that's interesting. Okay, that may do a pretty good job of what we want. Okay, and it turns out that if you do the average of the LRA and the RRA, right? If you do the LRA plus the RRA all over 2, what's the average of 30 and 50? Wait, 30 and 54? What's the average of 30 and 54? 42. What was the exact value I gave you? 41 and a third. That's pretty good, isn't it? That sounds pretty good. All right. Maybe not from NASA, but this sounds pretty good. All right. Okay. So if you average them, okay, that may very well be better. Now you might ask, is there a single rule that does that for us? Actually, there is. It's called the trapezoidal rule. And we'll talk about this when we get there, the trapezoidal rule. That's the thing we're going to do next Monday in 5.7, using trapezoids. Okay? First of all, what is a trapezoid? Try to remember what a trapezoid is, and try to think about why it is that the average of the LRA and the RRA gives the result that trapezoids would have given us if they have slanted heights, pieces of secant lines as our tops. We're going to do that next Monday. Okay. This is equivalent to that. If anything, the trapezoidal rule is a shortcut way of doing all this, doing the averaging of the LRA and the RRA, and as is the case here, we hope that the result will be much more accurate. Okay. We'll talk about the trapezoidal rule next Monday. Any questions so far? Sure.
It seems almost like a sequence or a factorial. Like we have like a factorial or factorial, and then maybe
Not so much factorial, but a summation. It's a summation, right? And then you get a pattern going. Right, right. So yeah, it's like summation. It's like a summation I squared times delta I kind of thing. You know, that kind of thing. You know? Yeah, yeah. So we're going to talk about that. We're going to talk about how to relate this to sums. We're going to talk about how to define this using a limit of sums. Okay. And factorials that comes up in, well, not so much with integrals, but with series later on. But yeah, the idea of series, the general idea of series and sums. All right. Okay, series with factorial you deal with when you're doing expansions for sine of x and cosine of x and all that. All right. Now a third scheme, and this is another candidate for a pretty good approximation. All right. Third, how about an MRA? Okay, not MRI, MRA. All right. What's the scheme there? On a subinterval, don't take the left midpoint, don't take the right midpoint. How about the midpoint? All right, this is the midpoint Riemann approximation, or a midpoint Riemann approximation. Depends on what the partition is. If you have a different partition, you have a different approximation. Okay, midpoint Riemann approximation. So in each of these subintervals, we're going to stand at the midpoint. Okay, now the result may not be the same as for the trapezoidal rule, but we hope that they're both close. Okay, it's kind of a compromise, right? Especially for functions that you know are monotonic, meaning always increasing or always decreasing on an interval. All right, let's draw the picture again. How does the midpoint guide work? X-axis, y-axis, we hope he also does a good job. All right, here's 1, here's 5, here's 2, 3, 4. All right. I want to approximate this area. On the first subinterval, from 1 to 2, what's the midpoint there? 1.5. Or 3 halves, whatever. All right. 1.5. We look up, we take this point on the graph, go left and go right. Okay. As it turns out, he's going to be a bit of an, so let's see, a smaller gap here. So we have more of an excess than we do a gap. Okay, so he's probably a slight underestimate. He's a very slight underestimate because what we lose here is not quite made up for by what we gain here. All right, that's because of concavity. All right, but it's really pretty close. All right, second one, between 2 and 3, we have 2.5, right? Look up, 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 up. Between here and here, we have 3.5. Okay, look up, go left and right. Between 4 and 5, we have what? 4.5, look up, go left and right. Okay. You agree this is probably going to do a better job than either the LRA or the RRA. Let's see how he stacks up against their average then. Okay, so we're going to take the sum of the areas of these rectangles. And by the way, nothing's negative here, so we don't have that hassle. Well, it's not that much of a hassle. I mean, if there's a negative contribution, there's a negative contribution. So even if this function goes negative, it's not that big a deal. Okay, the general formatting still works. All right. So what's the MRA going to look like if we have a regular partition of 4 subintervals of that interval? All right. So the MRA here, okay, is going to be, all right, f of, okay. So where are we standing between 1 and 2? 1.5. So f of 1.5 times 1, the width, plus f of 2.5 times 1, the width, plus f of 3.5 times 1, plus f of 4.5 times 1. All right, this is going to be, remember the function value the function is a squaring function, very easy function rule. We're going to square these inputs. Bear in mind, it could get more complicated, right? Obviously, if you're doing an approximation problem, the function you're dealing with might be either difficult or not well known. It's from an experiment. All right, but here we have 1.5 all squared times 1. I put the times 1 just to remind you that the width might not be 1. Okay. 2.5 squared times 1 plus 3.5 squared times 1 plus 4.5 squared times 1. Okay. And of course, there was something similar for the RRA. I didn't want to be tedious, so here it looks kind of weird, so I didn't want to write it out. If you work this all out, you're going to get 41, which is actually the winner in this case. I wasn't sure, but in this case, this is the winner. He's the one who's actually closest. Although, there are cases where the LRA is best of all these schemes, so it depends on the function. Right. But you would think that the trapezoidal rule and the MRA would tend to do the best job, especially if you have a monotonically increasing or decreasing function, because the LRA and the RRA tend to be too biased in one way or another. All right. So this happens to be the winner, although that's not always guaranteed. All right. Questions? And again, it's a very slight underestimate because we lose a little bit more than we gain as an excess.
So when do we know if we could use the MRA or the?
I'll tell you.
Okay.
I'll tell you what's needed. But you should know what I'm talking about. Like if I say a regular partition, you better know what I'm talking about.
Okay.
But no, so basically I give you no choice. I mean, I'll tell you to do it one way, you do it. You figure out what I'm talking about, you do it. All right. Anything else? Anything else? Okay, so it's not like it's not win a prize. The person who gets close to win a prize. All right. So questions about those approximation schemes? Again, in theory, a fourth grader can do this if the fourth grader knew function notation and all that. A bright fourth grader, very bright. Bill Gates' kids, huh? Well, those kids from Me, Myself, and Irene. You put the electron here. Right. All right. So, how can we describe this in general? What's the general format for a Riemann sum? These are all examples of Riemann sums. Okay, these are Riemann approximations of definite intervals. All right. what's an example of, what's the general format of Riemann sums? Alright. So right now, this is just an approximation, okay? So everything we've done so far is going to fall under this scheme, right? So we have the integral from a to b, f of x dx. Assume for now a is less than b. Okay, we will relax that later on. Okay. We're going to approximate that by what? Although here, there's no guarantee that they're close, but the word close is subjective anyway, right? Okay, so we're going to approximate the value of this definite integral, if it exists, by the following sum. All right. Now, you folks agree that in all of these cases, we've been taking the sum of areas of rectangles, right? We've been adding up the areas of rectangles, right? Okay. So, summation. Now, here's our index of summation. That's a dummy variable. I don't care what you call it, right? Summation k equals 1 to n, all right? N is the number of subintervals. Okay. Or number of rectangles. Bearing in mind, they could go flat if the function value is 0, where you're standing. Okay. Okay, but summation k equals 1 to n, where n is the number of subintervals. They're usually rectangles or they're flat if your function value is 0. Okay. All right, now, as our summand, we want the signed area. Okay, remember, if it's below the horizontal axis, we want it to be a negative contribution. It's the signed area of the kth rectangle, okay? Whether it's the first or second or third, over to the end. Okay. Well, what's area? It's basically height times width, right? The way we're setting it up, height times width. Well, it's a signed height, right? It's a signed height because it could be positive, 0, or negative. Okay. So we want the signed height times the width. The subinterval, the rectangle. Now, what gives me the signed height? What's the notation? What's going to be in the notation if I want the signed height? F of whatever. Yeah. F of, well, what is that whatever? All right. You know what? Here, if you put x of k, then that's going to be a right-hand Riemann approximation automatically. I'm going to say w sub k. What? What's a w? Okay. Where w sub k is in the kth subinterval. Okay. Remember, in the subinterval, right? You can stand anywhere you want. It could be the left endpoint, right endpoint, midpoint, or some random choice. In fact, in Mathematica, you could have a random selection. All right. But when you're in the kth subinterval, you can stand anywhere you want. All right. But you agree that that doesn't have to break the rules. Do you accept the idea that you can stand anywhere you want in the subinterval? Right? So, f at, let's say w sub k. Bear in mind that if it's an RRA, right, if it's an RRA, then it's always going to be x sub k. If it's an LRA, it's actually going to be x sub k minus 1, where x naught is a, x sub 0 is a. For an MRA, you're in the middle. It's the average of these. All right. And again, there's a random possibility on Mathematica. Mathematica can pick a random point within the subinterval. All right. So it's the function value at some value in the subinterval. It can be the right endpoint, left endpoint, midpoint, whatever. All right. Times the width. Width. Small change, small width. This should be no surprise. Delta x sub k. Where delta x sub 1 is the first width, delta x sub 2 is the second width, delta x sub 3 is the third width, and so forth. Oh, there you go. That's a Riemann sum. Okay, summation, k equals 1 to n. K is a dummy variable. I don't care if you call it I or j or whatever. All right, k equals 1 to n. There are n subintervals. All right. The signed height is f of wk. Here we stand at the midpoint, right? 1.5, 2.5, and so forth. So here, that's, okay. So over here, this is w1, that's w2, w3, w4. So what's the anatomy of this thing? x naught, x sub 0. That's by convention. B is x sub n. In this case, x sub 4. There were 4 subintervals. This is x sub 1, this is x sub 2, this is x sub 3. And these define the partition. All right? For an M array, all right, here's W1. That's where we stand. That's where we take the function value. It's like a sampling, like in statistics, like a sampling. All right? Here's W2. Here's W3. Here's W4. Again, for an L array, you stand at x0, x1, x2, x3. For an R array, you stand at x1, x2, x3, x4. Right? And for the M array, you take the averages of those guys. All right. But that's sort of the anatomy of the notation there. Questions about that?
What does delta x sub k mean? I understand what it stands for.
Yeah.
I'm what it
It's the width. Delta x1 is here. Here's delta x2. Here's delta x3. Yeah, thanks for reminding me. This is delta x3, and this is delta x4. Okay, they're the widths. Bear in mind, they don't have to be equal. Okay, in principle, they don't all have to be equal. Right? If they are equal, we have a regular partition. But not all partitions have to be regular.
I apologize. Why delta?
Delta is our classic, a capital delta. It's our classic choice for like an increment or a small change in. It's like a small change in x. Right, understand? Like for example, why do we sometimes call it derivatives dy dx? Because they're related to slope, delta y over delta x. Right? What's the change in y for every small change in x? Right. So slope is often and derivatives are often approximated by delta y over delta x. Right. That's capital delta. Indicates like an increment, small change in. All right. Questions? Understand that general format. Could this be on the test? Yeah, I could ask you, give me the form for real on some. That's fair. It's not too bad. Come on. Summation, k equals 1 to n. Function value at the places where the kid stands times each of the widths. It's not that bad. Conceptually, it's not that bad. Huh?
So, if I wanna plug the RRA, I mean, or LRA, then should I put k minus 1 in the count?
Well, yeah, here's a scheme. For an RRA, what I'm saying is that WK is x sub k. All right? So W1 is x1, W2 is x2, W3 is x3, W4 is x4. All right? For an LRA, that means that WK is x sub k minus 1. And for an MRA, WK is the average. Now, of course, this is getting very deep. I'm not going to ask you to write these down explicitly, but these are easy schemes by which we obtain these W's, the places where we stand. Okay. Again, in principle, like Mathematica, it gives you an option where the W's are random. They're random places in these subintervals. In principle, that's fine. Okay, I wouldn't ask you to do it that way, but I would ask for an LRA or an RRA or an MRA for a Riemann. I wouldn't have you do it by random or something. I'll mix them up. So some of you might be going, wait a minute, couldn't x1 be used twice then for a random? Yeah, it could, in theory. Right. Okay, questions about that format? If you understood the 3 examples, they all fall under this format, right? It's just that we stand at different places, right? And the widths were all the same, they're all 1. That was easy. In fact, I'll make that comment. In example 1, okay, P, the partition, was regular. It was a regular partition. Okay, regular meaning that all the x of k values, all the delta x k values are equal. Okay, all the widths are equal. They're all 1 in all 3 of our examples, the LRA, the MRA, RRA. Bear in mind, they don't have to be equal. You can have a non-regular or irregular partition. So if it's not regular, it could look like this. Maybe this is A, this is B, and it goes boom, 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 boom. It's like Homer's heartbeat right there. That's fine. No one says that you have to have equal widths. It's just sometimes convenient. Now, bear in mind though, if it's a regular partition, and if I give you n, you should be able to figure out the widths, right? should be able to figure out the partitions. All right? For a regular partition, all right, if the partition P is regular, then what's the formula for delta x? All right? Delta x is the common value for delta xk. Delta x, which is equal to each of the delta xk's. If all the delta xk's are equal, we just call them delta x, right? You can forget about the subscript, right? Then this doesn't depend on the subscript, right? If you have a regular partition, right? What's the formula for delta x? Well, let's say you have a big piece of licorice, or a good candy. I don't know if you like licorice, but you have a big Twizzler, a big piece of candy, right? Okay? It's going from A to B, right? A less than B. How long is the licorice? Here's A, here's B. How long is it? B minus A, right? Okay. So delta x is going to be B minus A, and let's say you have n kids. You go on Maury, and Maury tells you have n kids. Right. Whatever, 4 kids. You have 4 kids. And he goes, all right, you're home. All right, B minus A all over A. Right. So if you have 4 kids, right, you have to take this big stick of licorice, right? You'll get this big Twizzler, and you cut it into 4 equal-sized pieces. The delta x, the common value for delta xk, will be B minus A all over N. You should know that, right? You take the whole interval, divide by N, and that'll give you that common width. All right. And then, it's kind of like the way I taught trig. It's like an increment, right? You start at A, which was 1 in our example, right? And you keep adding that delta x. So if delta x is 1/2, for example, it'll be 1, 1.5, 2, 2.5, 3, and so forth. So you keep adding it until you get to B. All right. And of course, if you do this right, you will reach B and end there. Okay. So if you do this right, you will run into B. That's it. All right. 3.5, 4, 4.5, 5. All right. Questions? Questions? So you agree, it's okay for me to ask you, okay, for an LRA or an MRA or an RRA, for the integral of some guy from A to B, right, using a regular partition with a certain number of subintervals, right? Whether it's 4, 5, 6, 7, whatever, right? And you can figure it all out. All right? Figure out what the width is, the common width, and then you can figure out what the partition is. All right? So for a regular partition, I just have to give you a few bits of information. Right? Whereas for I don't know if they call it non-regular or irregular. For a partition that's not regular, I would actually give the partition. Okay, the partition is what? 1, 3, 3.6, 4.9, and 5. Just because that's the only time when we took these measurements. Those are the only time when we took the measurements. All right. Okay. Questions? Questions? N is the number of subintervals. Okay, so yeah. So here's A, here's B. Okay, the overall width of the licorice is B minus A. If we break it up into n subintervals, 1, 2, yada yada, n, all right, then each of these widths is the common value for delta x, which is B minus A all over n. Okay, so that's a good picture to draw. And of course you can figure it out, right? Because you'll know what A and B are, they're on the integral, right? And I'll put constants, I'll be nice, I'll put constants, numbers, actual numbers, okay? So you don't have to give me some weird expression as your final answer. Okay, you'll get numbers. And with practice, people tend to do well on this. All right. Let's do any other questions, by the way? Any other questions? Let's do a second example. All right. And then we'll officially define what a definite integral is. All right. Example 2. Here's an example where I give you a bunch of information, but you have to know how to put it together. All right. And again, this is kind of like a physical experiment where you don't know what f of x is, because the world is not made of, fuzzy. Well, I guess we do have some fuzzy bunnies, but the world is not full of fuzzy bunnies and f of x equals x squared. We sometimes have f of x equals x squared, but that's kind of convenient, right? Sometimes we don't know what f of x is. Maybe we have to do a statistical model. All right. But anyway, let's say our goal is to find an LRA for the following integral. The integral from determined by the following ordered set. Okay, so where are the fence posts for this thing? Basically, when do we make our measurements? Okay, when do we take our measurements? Let's say we take 4 measurements. Okay, 0, 2, 5, and 6. We're integrating from 0 to 6. All right. But I only have to give you 3 of these function values in order to find an LRA. Okay? Now, based on this partition, okay, I actually don't need which function value, f of what, for an LRA. We don't need f of 6. Okay, the RRA needs him, but not the LRA. So I'm going to give you f of 0, f of 2, and f of 5. I'll give you these function values. Okay, so what are these measurements? Let's say f of 0 is 3, f of 2 is 4, f of 5 is negative 2. All right, I'm just kind of throwing them at you. So what does our partition look like? All right, so here's 0, here's 6, okay, here's what? Here's 2, here's 5, all right? And I'm giving you, it's an LRA, and I am giving you f of 0, f of 2, and f of 5. We have 3 subintervals, n equals 3, but this is not regular. It's not regular, because obviously there are different widths. Okay, but you see here we have a partition of the closed interval from 0 to 6, okay, into 3 subintervals, all right? We're doing an LRA because we're given the function values at the left endpoints of these 3 subintervals. I did not need f of 6. We would need f of 6 for an RRA, not the LRA. All right, questions?
Was the n given? Or-
Well, the n is implied by the nature of this partition. If you have 4 fence posts, they close off 3 subintervals.
Okay.
Okay, you draw a picture here, right? 1, 2, 3. This is W1, this is W2, this is W3. All right. All right, so let's do the LRA. Let's do the LRA. All right. And we can draw a picture just for kicks. All right, X, Y. All right. So we have 0. I'll do it this way. 1, 2, 3, 4, 5, 6. All right. Here's 2. Here's 5. Here's 6. Okay. F of 0 is 3. What does that tell me about the graph of y equals f of x? F of 0 equals 3. What does that tell me about the graph? The point 0, 3 lies in the graph, right? Of y equals f of x. All right. So 1, 2, 3, 4. Okay. So 0, 3. F of 0 equals 3. Okay. F of 2 equals 4. What does that tell me? 2, 4 lies on the graph. All right. F of 5 equals negative 2. All right. Over here, negative 2. Right. 5, negative 2 lies on the graph. All right. So we're given very limited information here. All right. Well, come on. What's the best job we can do? Well, according to the Riemann scheme, let's use rectangles, and let's do the best job we can do with what we have. All right. From 0 to 2, well, let's take this guy. We look up, right, and over. Okay? How at this point? Well, at the 2, we look up, right, all the way here, and down. Okay. Now over here, we look down to this point, then to the right, then up. So for the first time, we actually look down. Okay, because the function value is negative there. All right? And basically, our approximation for the definite integral will be the sum of these signed areas. All right. Now I'm going to bring in the notation. All right. So our LRA is given by the following. All right. We take f of 0. Okay, that's f of W1, right? F of W1. Now, in fact, you know what? I'm going to actually write this. I'm going to write out the general form. Summation, k equals 1 to n. Well, n is 3 here. All right. F of wk delta xk. I need the subscript because these widths are different. All right. Well, let's write this out. F of W1, the first place we stand, is at 0. Okay? Times, what's delta x1? What's the width of this first subinterval? 2. Okay, I can do it here, right? Maybe I should have, okay, well, this is 2, 2. I'll write it out. Delta x1 is 2. Delta x2 is 3, right? Delta x3 is 1. All right. F of 0 times, it was 2, right? Okay, 2. Plus, see, plus summation. F of, what's W2? What's the next place we stand? We stand at 2, right? We stand at 2. F of 2, all right, times, what's the width? 3. F of 2 times 3. So here, W2 is 2, delta x2 is 3. Plus F of, the last place we stand is where? At 5, that's W3. Okay, times, what's the width of that rectangle? 1. All right, you see, this format fits this, right? Okay, we're adding up, right, what? These sine heights, these function values, times the widths of their corresponding subintervals, or rectangles, right? Makes sense. Sine area, sine area, sine area. All right, what is F of 0? I gave you it was 3. So it's 3 times 2. Plus F of 2 is, that's 4, all times 3. Plus F of 5 is negative 2, all times 1. All right, so see what's happening here. All right, first rectangle, what's the sine area? Well, what's 3 times 2? It's 6, and it comes in as a positive 6. What's 4 times 3? That's 12. That comes in as a positive 12. Now, what's negative 2 times 1? Negative 2. Why is it negative? Below the x-axis. Yeah. So that contributes a negative 2. All right? Okay, so 6 plus 12 minus 2, 16. Right. That's our approximation. 16. Okay. So that's like if you're given limited information, you're doing a physical experiment. Bear in mind, we may not ever know what the graph actually looks like. We might not ever know what f of x is the closed form. Okay? I don't know, maybe the graph looks like this. I don't know. I don't know. Well, I mean, this graph, he's, he would work, right? Goes from this point, to this point, and this point, right? It's nice he's continuous, you agree? It's nice if he's continuous. We assume that way. We assume the bird is not like magic. Okay. All right, questions? Questions? Don't be afraid to draw little pictures to get a sense of what's going on here, right? Really, we're just adding signed areas of rectangles. We're using kind of booky notation, but it's not that bad, right? We're basically adding up the signed areas of rectangles, right? Remember, the function value could be positive, 0, or negative. Okay, questions? Questions? One question I can ask you on the test, on this quiz, or on the final, what is the limit definition for a definite interval? And this is the way that we formally define definite intervals. All right, issue E. The limit definition. Of a definite interval. We're going to use Riemann sums to do it. A limit definition of a definite integral. Oh, okay. In fact, let me leave this example over here. Yeah, I'm going to refer to this anyway. All right. Okay. Now, here's a question. When do we expect our approximation to be better? Like I remember someone, I think Don was asking, that earlier example, what if we went from 1 to 1.5 to 2 to 1.5, right? Basically, if the partition is finer, right? We're sampling more points, right? Okay. But here's the thing. What's a single number that can measure for us how fine a partition is? Okay. Now, when I say how fine, I don't mean hot or not. Okay, I mean that fine. I mean, how fine is this partition? How thin are these subintervals? All right. What's a single number that'll do it? Okay, this is called the norm. All right. Double bar, P, and again, normally we use a cursor. All right. Double bar for norm. Okay. Some of you might remember this as like length of a vector. Yeah, that's okay. It's a measurement of. It's like a physical measure. Okay. The length or norm of a partition. In this case, the norm of a partition. All right. The norm of the partition P. What is this formally? Formally, it's the maximum over all k's of the delta x k's. Okay, Okay, it's the max of those delta xk's. What do I mean by that? It's the widest width. It's the widest width of all these subintervals. All right? The widest width. So for example, look at the example we just did, right? Well, 2, 3, and 1. Which one's the widest width? 2, 3, and 1. 3, right? The distance between 2 and 5. Okay? So here, in our last example, okay, in our last example, example 2, the norm of the partition was 3. Okay, the distance from here to here. You know the old phrase, a chain is only as strong as its what? Its weakest link. Well, a partition is only as fine as its widest subinterval. That's like the worst guy, right? The widest subinterval. That means that I don't have very fine information in here, right? It means that it's kind of a no man's land from here to here. Okay, it's like you have to cross a desert to go over to the next outpost. Right? So it's kind of a no man's land between 2 and 5. That's the widest width. He's kind of the weakest link. He's the worst guy. Okay. Because, you know, with 5, those were close to the endpoint there, right? 6. All right. So that's a measure of how bad your partition is. Okay, how grainy it is. Okay. So once again, the norm measures how fine the partition is. Okay? And generally speaking, we want it to be lower. If we're aiming for accuracy, we'd like it to be lower, so that we're taking the measurements more frequently. Right? Okay. So that delta x, for example, is more like a half as opposed to 1, let's say. All right. So now, what is the limit definition of a definite integral? And this is going to be exact. All right. The limit definition of a definite integral. And I could ask this on the quiz or the final. All right. The integral from a to b f of x dx equals, and I mean equals, the integral from a to b f of x dx. All right. It's a calculus class. What was the first concept we learned as a calculus class? It was that L word. Limit, right? Limits make calculus calculus, right? It's the limit of these Riemann sums. And it's the same guy you dealt with before, right? You can just put summation over k. You don't have to put from k equals 1 to n, all right? It's sort of implied here. Summation over all relevant k, all right? Of f of wk, right? Times delta x of k, where wk is in the kth subinterval. All right. Now, basically, I'm repeating the definition of a Riemann sum that we did back then. All right. Remember, this thing here is the signed area, right? Signed meaning plus or minus. Is the signed area of the kth rectangle. Okay. Bear in mind it could be 0. In which case you have a flat guy. All right. If it's signed, that is plus or minus the area of the kth rectangle. That's the summand. All right. Now, what will give us the exact value? Take the limit of these partitions. So think of a sequence of partitions. Imagine a sequence of partitions. Okay, they don't have to be regular, all right? But here's one partition, kind of chunky, kind of grainy, right? Here's another one. The norm's smaller for this one. Here's another one. Okay, the norm's even smaller for that one. Right? See what I'm getting at? You agree that it's more likely I'm going to get a better approximation if I take all the function values over here, right? If I do the approximation using thin rectangles as opposed to thick rectangles, right? Okay, that's the general tendency. It's not always the case, but it's the general tendency that if you have these smaller subintervals, that you're going to do a better job, right? And by the way, there are applets. If you check my chapter 5 notes page on my website, there are applets that show you sort of these little graphical animations that show this process. All right. So what do we want? Well, we want to take the limit of these Riemann sums. So, this gives us a sum, right? This gives us a sum. This gives us a sum. This gives us a sum. We get a Riemann sum from all these guys, right? We take the limit of these Riemann sums as the norm, or norms, of these partitions approach what number? The width. The width approaches 0. Okay. Actually, you might want what to approach infinity. Not the norm, but sums as the norms of the partitions approach zero. Some folks don't stress the fact that we're talking about, in principle, a sequence of partitions. Okay, have to get finer and finer and finer. Okay, do you buy that idea? That idea. I have a couple more comments. Well, the value of this is this if the limit exists. Right, so I guess my box might include this piece as well. But if the limit exists. You agree there might be cases where the limit does not exist. Okay. So, for example, if this is A, this is B, vertical asymptote, right? You agree that we might have a problem here, right? We might have a problem here, right? Okay, we agree on some? So, we don't like these kinds of discontinuities, especially infinite ones. However, in Calc 2, in Math 151, you handle these. And in fact, sometimes the definite integral will have a value if these branches approach the VA fast enough. So it's possible that these guys might never actually touch the VA, but it's possible you might get a finite real number. That's possible. It depends how fast you're approaching. Depends. So that's a Calc 2 issue. Does the integral converge or divert? That's a calculus issue. Right. If the limit exists.
So you want that inside the box? If the limit
Well, yeah, okay. I will mark it down now, but it equals the limit if the limit exists. All right. In which case we say, okay, in which case we say that f is, you remember how we used the word differentiable before? Now it's integrable. If f is integrable on the closed interval from A to B. Differentiable means that we can take the derivative and the result's a real number. Here it means that we can integrate like so, and we get a real number result. Okay, f is integrable. But then you might be asking, well, wait a minute, how do we know that a function's integrable? Well, I will give you a key sufficient condition, and it's an old word. It starts with C, a property we love, continuity. If we have continuity on the closed interval, we're guaranteed integrability. That's great. So, if f is continuous on the closed interval, then f is integrable on the closed interval. And there will be a value for the corresponding definite interval. So, if I ask you to work out a definite integral, your integrand will either be continuous on the integrand, on the interval, or there might be a jump discontinuity. Actually, if you have a jump discontinuity, you can control that. But that's not really that much of a problem. Okay, so jump discontinuities are actually okay. All right, infinite discontinuities, that's a Calc 2 issue. That's much more problematic. Right. You can have a finite number of jump discontinuities. That's not a big problem. Now, I want to mention a final comment. So you can, you can kind of box this in as a separate box. I'm not going to harass you on these issues. That's Calc 2. In Calc 2, you'll be harassed on these issues. Okay, I wouldn't harass you on these issues in Calc 1. Okay. Although, I might give you a function that's piecewise continuous, if not fully continuous. Now, here's the deal. Some of you were saying, well, you know, we have these partitions, 1, 2, blah, 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 n. Okay. Why not just let n approach infinity? Some of you might be saying, well, why can't we just say let n approach infinity? Why do we have to go through this bother of defining a norm and letting it approach 0? Why not just this? Here's the problem. Here's A, here's B. All right, first partition. All right, first partition. Okay, fair enough. Second one. And then, you know what I'm getting at here. What am I getting at here? I might make this side nice and tidy. He's just sitting there. You see? It's not sufficient to just let n approach infinity because you still allow junk like this to happen. You're still going to have a problem picking up this excess over here, right? Or this gap that we're missing from what we need. What will prevent this guy from just sitting there like a big old lug? Well, that condition. You agree, if we force the norm to approach 0, this guy has to break. why we want this condition, so we avoid situations like these where, yeah, we might be great over here, but then this guy's just sitting there. We want to avoid that. Now, when is the condition n approaches infinity sufficient? If we have continuity, for example, and if the partition is what kind of partition? If it's regular. If it's regular, then the condition at n approach infinity, that is hand in hand. That's equivalent to saying that. Okay, that's cool. Just some side notes there. All right. We can go through, or you can go through, that 5354 block. We're done through there. You wouldn't need the homework, by the way. We're done through the 5354 block. We'll do 55 and 56 on Wednesday. 57 is next Monday. You'll have your test next Wednesday, I hope so. I'll be over.